As many of you probably know, it is done by measuring with the Doppler shift the wobble of stars. Now, just to give you a quick idea of what this wobble is all about, again, when I went to school, of course, it must have been a long time ago, of course, but because I'm older than dirt. But what we're looking at here is I was once told, and perhaps again some of you may have also been, that the planets, our planets, orbit the sun. To a first approximation, that's okay, but to be really accurate about it, or more accurate about it, that's wrong. There's a better way of describing it, and it is better to think of this better. It's still not exactly physically accurate, but it's better to think of planets orbiting a center of mass of the system, and also the star itself orbiting the center of mass of a system. If there are planets, they orbit a center of mass. And if there are planets, the star also orbits the center of mass. And we view that orbit of a center of mass by the star as, of course, its wobble. If stars wobble, it's because somebody else is there. That there are other objects in orbit around that star that cause it to wobble. And this is shown here in this cartoon, showing a planet orbiting in a clockwise direction here, and a star, of course highly exaggerated as you'd expect, but a star orbiting in this way as well, wobbling. What's going on? Let's imagine that the planet is here. The star is over here, and between them, somewhere between them, there is a center of mass. I like to imagine in an analogous way of this being a teeter-totter. A teeter-totter or a balance beam or whatever it is. I don't know what it's called in Rhode Island. What's it called? Seesaw. It's a seesaw. It's a seesaw. So you end up having a balance point where, of course, you put the high mass thing in close to that balance point, and the smaller thing is out further from a balance point. You get this balance on the seesaw. Well, that you can think of it. It's a helpful way of thinking about this problem here, because if the planet is here, and the center of mass would be there, toward the center of each of these orbits, then the star would be on the exact opposite side of the center of mass from the planet. Now, as the planet moves around on its orbit, what's happening to the star? The star will be moving over, always keeping the center of mass between it and the planet. Always maintaining that balance. Now, this is for a two-body problem. As you'll see, it becomes more interesting when there are more than two bodies to be considered. But we're looking here then at the source of the wobble in a star that is being measured by these really outstanding astronomers is the notion of a center of mass around which both the star orbits and the planet orbits. Now, for a two-body problem like this, what you're looking at then is the period of the planet's orbit is going to be equal to the time of the wobble of the star, that they are hooked together effectively. So if it takes 1 Earth year for the planet to go around the center of mass, it would take the star 1 year to go around the center of mass as well. They're tied together. As of about a week ago, notice 194 planets had so far been detected. 194. Using this Doppler approach, in which, notice, with very sophisticated technology and methods here, as the star wobbles toward us, light is shifted to the blue. As the star wobbles away from the observer, it's shifted to the red. So we're looking at a very sensitive Doppler shift, in which the most remarkable thing here, of course, is the accuracy and precision with which this Doppler shift can be measured. Measured to plus or minus 2 meters per second. 2 meters per second. Our relative speed, the speed of the star's wobble toward us or away from us, can be measured by these experts here to an accuracy of plus or minus 2 meters per second, which is equivalent to about a fast walk. Meanwhile, we're ripping around the sun at several kilometers per second. The moon's, of course, what's the moon doing to the Earth?
Same thing.
Same thing. So the Earth's doing this, as the moon goes around it, and stars are moving with respect to each other as they're moving through the galaxy as well. So you have to understand all of those different vectors in order to extract, then, of course, the motion of the star that you're interested in to an accuracy of 2 meters per second. That's not bad. So notice we're approaching 200 planets known, around 97 stars. Hundreds of planets are being monitored. And soon, with the launch of several other spacecraft by both NASA and the European Space Agency, the number of stars that will be monitored will be in the many thousands. Here are typical data here, and just to give you a sense, many of you may have seen these kind of data, but let's take a look at it and see what it all boils down to. Here is one planet orbiting one star right here. What are we looking at? We're looking at time, that is, start of an orbit, end of an orbit. So that's just one orbital period here, which in this case is 3.971 Earth days. There's a planet going around this star that orbits that star in less than 4 Earth days. Let me imagine what it's like.
It's over.
Giordano Bruno hot.
Yeah, right.
This you can see that's a bad place. But it shows up on the star's wobble. Again, this is effectively time, where that to there is just about 4 days from here to there. And this is wobble speed in meters per second. And the vector here is toward us and away from us. So it's blue shifted and red shifted at certain meters per second. So the star was coming toward us, going away from us, toward us, and you can see that the amplitude of the signal is around 30 meters per second, 30 meters per second, about 100 feet per second at maximum moving away from us, and about 100 feet per second moving toward us during that star's wobble. Notice that the data can be fit pretty well by what appears to be, of course, a sine curve. The amplitude, notice the total amplitude of the wave that's being shown here is roughly 70 or so meters per second. The kind of information contained in here is this. The sine curve tells you that it's a circular orbit. It's a circular orbit. Eccentricity of the orbit, zip. The time between just select any point on that curve and find the equivalent point further along on the wave. So let's choose here, for example, to here. That is the what?
Period.
The period of the orbit and of the planet's orbit, and of course the period of the star's wobble. They're the same. So we're looking here at 4 days. From here to there is 4 days. So you've got the orbit. It's circular. It has a period of 4 days. And what's the mass, or at least the minimum mass, of this planet? That's contained within the amplitude of that signal. If it had been a dweeby planet, a real dweeby